Hello and welcome to my science tutorials. In today's video, we want to attempt the solutions to the homework that I gave earlier on magnetic flux and magnetic flux density. Now, if you've not watched that video, you can watch that video as part of our magnetic circuit tutorial. So you can go to our playlist, look for magnetic circuit, and then you can find that over there. So the topic then was magnetic flux and magnetic flux density, and I gave 3 homeworks over there. And then in this video we'll look at the solutions to that particular problem. All right, so let's look at the first question that we have. So the question is, what is the flux density in a magnetic field of cross-sectional area 20 centimeters square having a flux density of 3 milliweber? Okay, so I'll write down the solution to this problem. So solution. So what is the flux density in a magnetic field of cross-sectional area? So the area over here is 20 centimeters squared, and we were given a magnetic flux of so our magnetic flux phi is equal to 3 milliweber, which is equal to 3 times 10 raised to the power minus 3 Weber. Very good. And so we are to calculate the magnetic flux density, which is B, and that is what we do not know. Now note that magnetic flux density B is equal to magnetic flux, which is phi, over the area. Okay, and in this case we have our phi given to us, and then we have our area given to us. Now the problem is that the magnetic flux over here is measured in Weber, and then the area is measured in meters squared, and then our area has been given to us in centimeters squared. So this is the only challenge for this particular problem. If you are able to convert your area from centimeters square to meters square, you can easily solve this particular problem. So we know that 1 meter is equal to 100 centimeters. So if I square this, okay, okay, I will have 1 meter square over here will be equal to 100 squared will give me 10,000. So this will become 10,000 centimeters square. So it means that 1 meter square is equal to 10,000 centimeters square. So if the question gives me 20 centimeters square, so this will be equal to 20 centimeter squared over here, and that will be equal to an unknown value. Let me represent that with x in meter square. So from here, all I have to do is to do a little bit of cross multiplication over here. This will multiply this, and then this will multiply this. Okay, so if I do that, 1 multiplied by 20 will give me 20 centimeter square multiplied by meter square, and this will be equal to this will multiply this, so this will give me 10,000 x then centimeter square multiplied by meter squared over here. Now mind you, we want to find the value of x in this case. So what I will do is that I will cancel the centimeter square from both sides because I want just the meter. So this is basically like just 20 is equal to 10,000 x. So I'll divide both sides by 10,000 by 10,000. Okay, so the value of x will be equal to 20 divided by 10,000, and that will be equal to 0.002. Then I have meter square as my answer. So the area in meter square is 0.002 meter square. Very good. So now that we have the answer for our area, we can proceed to solve our problem. So our phi is or our magnetic flux is 3 times 10 raised to the power minus 3 on the area, which is 0.002. So we'll have 0.002, or someone can convert this to standard form and have 1, 2, 3. We'll have 2 times 10 raised to the power minus 3. That is also the same. So if I compute this into my calculator, 3 times 10 raised to the power minus 3 divided by 0.002 will give me 1.5 Tesla as my answer for this particular problem. Like I said, the only challenge for this particular problem is how to convert, okay, how to convert centimeters squared to meter squared. And once you're able to do that, you can solve this problem easily. And this is how you do the conversion, right? So 1 meter squared is equal to 10,000 centimeters squared. And so therefore, if you divide whatever you are given in centimeters squared by 10,000 centimeters, by 10,000, you should get your answer, and you can solve your problem. All right, let's have a look at the next problem. So we are to determine the total flux emerging from a magnetic pole face having dimensions 5 centimeters by 6 centimeters if the flux density is 0.9 Tesla. Okay, so let's write down the solution to this particular problem. Okay, so we are to determine the total flux. So phi is what we do not know, and then we're given the dimensions. So dimension is 5 centimeters by 6 centimeters. Okay, and then the flux density, which is B, is given to us as 0.9 Tesla. So the first thing I'll do here is to change the dimension over here to meters. So 5 centimeters to meters, that would be 5 divided by 10, and then 5 divided by 10 . Okay, so from centimeter we go to decimeter to meter, so it will be 5 divided by 100, and so we have 5 divided by 100, that will give me 0.05 meters by this will give me 0.06 meters. So therefore the area, okay, will be length times breadth or width, whatever you want. And then our area here, we don't know which one is the length or breadth, but all we know is that it will be 0.05 multiplied by 0.06, and so therefore our area for this particular problem will be 0.003 meters squared. Okay, so now that we have the area, we know that the magnetic flux density B is equal to the magnetic flux phi over the cross-sectional area, or just the area. So if we want to find phi magnetic flux, we make flux the subject by cross multiplying, and if we cross multiply, we'll have phi is equal to BA or AB. So our phi will be equal to, the value for B is 0.9 multiplied by that of the area is 0.003. So 0.9 multiplied by 0.003 will give me 0.0027, and if I convert that to standard form, I'm going to move the decimal point 1, 2, 3 times, so I have 2.7 times 10 raised to the power minus 3 Weber as my answer for this particular problem. All right, so let's go ahead and look at the last solution, last problem. So we have the maximum working flux density of a lifting electromagnet is 1.9 Tesla, and the effective area of a pole face is circular in cross section. If the total magnetic flux produced is 611 milliweber, we are to determine the radius of the pole face. Okay, so as usual, I'll write down the solution to this problem. So I have here the maximum working flux density of a lifting electromagnet is 1.9 Tesla. So my flux density is equal to 1.9 Tesla. Okay, the area of the pole is circular, so we are dealing with a circular magnet. If the magnetic flux, okay, which is phi, is 611 milliweber, okay, this will be equal to 611 times 10 raised to the power minus 3 Weber as the conversion. We are to determine the radius of the pole. So the radius is what we do not know, but we know that the magnetic flux density B is equal to phi over cross-sectional area or area. But in this case, since we are dealing with an effective area of a pole having a circular cross section, our area in this case will be equal to what? Pi r squared. So this implies that my magnetic flux density B is equal to phi over the area now will be what? Pi r squared. So if I cross multiply over here, okay, this will multiply this and this multiply this. My phi will multiply 1, which is still phi. Then I have B pi r square. To just leave r square alone, I divide both sides by b pi. So this will cancel this. So my radius squared will be equal to phi over b pi, or pi b. Now I want my radius, not the square of it, so I introduce the root sign to both sides. So this will cancel this, and so therefore my radius is equal to the root of phi over pi b. Okay, all right, so this means that my radius is equal to the root of my b. The value of my phi is 611 times 10 raised to the power minus 3 on my pi and b. So my b is equal to 1.9, so I have 1.9 pi. Okay, so if I introduce this into my calculator, the root of 611 times 10 raised to the power minus 3 all on 1.9 pi, the root of all this ratio, will give me a radius of 0.3199 meters, which I can approximate to 0.32 meters as my answer. So this is how we solve problems on magnetic flux and magnetic flux density, and this is the solution to the problem I gave in that tutorial earlier on during our learning of magnetic circuit. So thank you so much for watching, and I'll see you in the next video where we'll be talking about more related to magnetic circuit. Bye bye.